So today, we are going to proceed with the presentation for the subtopic that I've given to you. But before that, I'm going to explain to you what is a truth table.
Okay, what is a truth table? Truth table is a table that provides a method for mapping out the possible truth values in an expression and to determine their outcomes. The table includes a column for each variables in the expression and a row for each possible combination of truth values. As you can see on the screen, when P and Q is equal to true, it is when both P and Q are true and false otherwise. When P or Q is false, it is when both P and Q are false and true otherwise. When P implies Q is equal to false, it is when P is true and Q is false and true otherwise. When P is biconditional with Q is equal to true, it is when P and Q have the same truth values and false otherwise. For example 1, construct a truth table for negation P and P implies Q. For this question, you need to list down all the variables in the question. For this question, we have P, Q, negation P, P implies Q, and negation P and P implies Q. For P, it will be true, true, false, false. For Q, it will be true, false, true, false. For negation P, it will be inverse for P, and it will be false, false, true, true. For P implies Q, it will be true, false, true, true. And for negation P and P implies Q, it will be false, false, true, true. For the second example, the question is create a truth table for statement P or negation Q. For this question, list down all the variables in the question. It will have P, Q, negation Q, P or negation Q. For P, it will be true, true, false, false. For Q, it will be true, false, true, false. And for negation Q, it will be inverse of Q, and it will be false, true, false, true. And lastly, for P or negation Q, it will be true, true, false, true. For the last example, the question is create a truth table for negation P implies negation Q. Like I said before, list down all the variables in the question. For this question, it have P, Q, negation P, negation Q, and negation P implies negation Q. For P, it will be true, true, false, false. For Q, it will be true, false, true, false. For negation P is the inverse of P. It will be false, false, true, true. Same as negation Q, it will be inverse of Q. And it will be false, true, false, true. And lastly, for negation P implies negation Q, will be true, true, false, true. So now, who's going to explain about arguments?
Me, madam. Argument is a list of a given statement called premises, followed by the final statement called conclusion of the argument. As we can see, premises, all the premises from premises 1, 2 and 3 are all called hypotheses, and the outcome is conclusion. One of the methods that we can use to solve the argument's question is rules of inference. Now, rules of inference are practical to determine validity of arguments involving more than 3 propositions. Each rule of inference arises from logical impression. Rules of inference are modus ponens, law of syllogism, modus tollens, rule of conjunction, rule of disjunctive syllogism, rule of conjunctive simplification, rule of disjunctive amplification, rule of contradiction, rules of resolution, rules of constructive dilemmas, and rules of proof by cases. For question number 1 for rules of inference, the question is prove the validity of arguments. Now for the question we have 3 premises. The first premises is H implies S, and the second premises is S implies Q, and the third premises is negation Q. So the solution for all the premises is first thing first, we list all the premises, and the number 1 is H implies S, number 2 S implies Q, number 3 negation Q. So for the number 4 premises, we are using the first and second premises to use the laws of syllogism, and we get H implies Q. And lastly, for the last premises, we use the third and fourth premises to use modus tollens, and we get negation H for our conclusion. For the second example, the question is the same, prove the argument is valid, but the premises is different. For this question, all the premises are P implies Q, Q implies S, R implies negation S, and negation P or R. So for the conclusion is negation P. So for this question, we are aim to get negation P as our conclusion. So for the solution for this question is same as before. We are going to list all the premises first. So number 1, we have P implies Q, and then Q implies S, R implies negation S, and negation P or R. So for the number 5, we are using laws of syllogism on premises 1 and 2, and then we get P implies S. And number 6, we are using the third premises to contrapositive, and we get S implies negation R. For number 7 premises, we are using the 5th and 6th laws of syllogism, and then we get P implies negation R. Number 8 premises, we are using the premises number 7 to use the definition of implication, and then we get negation P or negation R. And then next, we use the premises 4 and 8 to rule of conjunction, and then we get negation P or R and negation P or negation R. And then from the premises, we simplify and use the distributive law to get negation P or R and negation R. From the premises, we use the inverse law to simplify, and we get negation P or F naught. And then the last, we get negation P from the last premises and use the additivity. So negation P is our conclusion for these premises. Okay, for the last example, it's a bit different from the last two examples because we have a statement here that we need to change the statement into the premises first if we are going to solve it. So for the statement, if I drive on the freeway, I will see the fire. I will drive on the freeway or take surface streets, or both. I am not going to take surface streets. And for the conclusion is I will see the fire. So from the statement, we get W as I drive on the freeway, F as I will see the fire, S as I drive on surface street. From the statement, we can get W implies F, W or S, and negation S. So the conclusion from the premises is F. So to solve this question is, first thing first, we have to list all the premises. Number 1 is W implies F, number 2 W or S, and number 3 is negation S. For the number 4 premises, we are going to use the second and third premises and use disjunctive syllogism. And then from the rules, we get W. And then the last, from the first and fourth premises, we are going to use modus ponens, and then we get F as the conclusion from the premises. Now I'm going to pass to Mira.
Next, we're going to the laws of logic. Many logical laws are similar to the algebra laws. For example, there is a logical law corresponding to the associative law of addition. A plus in bracket B plus C equal to in bracket A plus B plus C times A plus in bracket B times C equal to in bracket A plus B plus C. In fact, associativity of both conjunction and disjunction are among the laws of logic. We have many of laws, which is double negation law, De Morgan's law, commutative law, associative law, distributive law, idempotent law, inverse law, identity law, domination law, definition of implication, definition of biconditional, and absorption law. For example 1, the question is, show the following expression is a tautology by using the laws of logic. The question is, in bracket negation, in bracket P or in bracket P and Q and R, close bracket and close bracket, and R close bracket 2 in bracket P or R close bracket. For this question, I will use equivalent identity for the first and second absorption law, De Morgan's law, associative law, commutative law, associative law again, idempotent law, inverse law, and finally the answer I use domination law. For the example 2, the question is simplify the following expression, and the equation you will see. For this equation, for the first step, I will use definition of biconditional, second commutative law, and then associative law, absorption law, and finally definition of biconditional. For the example 3, simplify the following question. As you can see the equation, for the first equation, I will use definition of implication, De Morgan's law again, distributive law, associative law, and finally simplification.
Let's take a break before that.
Okay, next we're going to chapter 3. For chapter 3 we have many methods, but for now I'm going to explain the contraction method. Contraction method is used when the conclusion involves an existential quantifier. The contraction method can be used if the conclusion B is in the form of B, there is object with a certain property such that something happens. Okay, now we're going to example 1. If P and Q are even integers, then 3P squared plus PQ is divisible by 2. And how we're going to answer that question is A, P and Q are even integers. B, 3P squared plus PQ is divisible by 2. By using definition 1, B1 is 3P squared plus PQ equal to 2K, which is K, all K is integers. A1 is let P equal to A and Q equal to B. AB is integer. A2 is 3P squared plus PQ, and we're going to replace the equation with the let P and Q, which is going to be 3 in bracket 2A square plus 2A times 2B, and then we're going to A3 to 12A square plus 4AB, and then we're going to factorize it and it become 2 in bracket 6A square plus 2AB, and then we're going to let 6A square plus 2B equal to C, which is C all integer, and for last A4, 3P to 3P square plus PQ equal to 2C, which is C also all integers, and lastly A4 is equal to B1. Okay, next example 2. Prove each of the following statement using the contraction method. Is the constructed object is unique. A, there is an integer x such that x squared minus 5s over 2 plus 3 over 2 equal to 0. And we're going to answer the question A first. For A, because of we don't know what is x, so B, x squared minus 5x over 2 plus 3 over 2 equal to 0. X is all integer. And because of we don't know the x is what, so we're going to construct x, which is we're going to x squared minus 4x over 2 plus 3 over 2. We're going to times it by 2. So it's going we're going to get 2x squared minus 5x plus 3. After that, we're going to factorize it. And after we factorize it, we're going to get x equal to 3 over 2 and x equal 1. And because of it's only one the integers number, so we're going to choose only x equal to 1. And we're going to replace x with 1, which is when we replace it, we're going to get 0. Therefore, A2 is equal to B. The construct object is unique. And the next is B. There is a real number x. And same equation, but the difference is x is real number. So first, we're going to construct x, and we're going to get the same 3 over 2 and 1. And this because of it on a real number, so we can choose both number. So we're going to replace x with 3 over 2, which is when we replace it, we're going to equal to 0. And when also we replace it with 1, we're going to get 0. So x for A5, x squared minus 5x over 2 plus 3 over 2 equal to 0 for x equal to 3 over 2 and x equal to 1. Therefore, A5 equal to B. The construct object is not unique. And last is example 3. Prove that if m and n are two consecutive integers, then 4 divide m squared plus n squared minus 1. For A, m and n are consecutive integers. For B, 4 divides m squared plus n squared minus 1. And B1 is m squared plus n squared minus 1 equal to 4k. K is all integers. And A1 is m equal to 2a, n equal to 2a plus 1, which is a all integers. Then we're going to replace it by m and n, so we're going to get 2a squared plus 2a plus 1 squared minus 1. And when we solve it, we're going to get 8a squared plus 4a. And we're going to factorize it equal to 4 in bracket 2a squared plus a. And for A3, we're going to let b equal to 2a squared plus a. B is all integer. For A4 is m squared plus n squared minus 1 equal to 4b. B is all integer. Therefore, A3 is equal, or we're going to say same with B1.
Next, I'm going to pass this to Nabil.
So forward and backward methods is a proof of technique that involve working on a proof from both directions. So from the backward is the conclusion, and from the forward is obtained from given definition and the knowledge. So this method can be useful as it can encourage reverse thinking, provide a way to change the process, and help to avoid missing opportunities. Without further ado, let's go to the example. So for the first example, the question is if fx, 2x and gx, 2x are both one-to-one function, then fg is one-to-one. So they want us to show the analysis of the proof. So the hint being given is A, function fa to b said to be 1-to-1 if only and only if fx1 equals to fx2 implies that x1 equals to x2 for all x1 and x2 in A. So the solution is we should find the hypothesis which is represented by A. So the hypothesis of this question is fx, 2x and gx, 2x are both one-to-one function, and the conclusion that going to be represented as B if fg is one-to-one. So from B we could write a B1 that we could say that if fgx equals to fgy, then xy, then x equals to y. So x equals to y, it can be put in B2. And for the next one, A1, we could write fgx equals to fgy, and then in A2 we're going to simplify it into gx equals to gy, and then we could also assume in A3 that x equals to y. So as you can see, we already obtained the same conclusion that being obtained in B2. So for example 2, if 3 divides n, then 2n squared minus 3n is divisible by 9. So we need to show the analysis of the proof only. So the solution is, for the first one, we need to identify the conclusion and also the hypothesis. So the hypothesis of this question is 3 divides by n, and the conclusion of it is 2n squared minus 3n is divisible by 9. So based on the conclusion, we could write 2n squared minus 3n equals to 9k, and k is element of Z. So A1, and then we proceed to the A1. So for the A1, we could make a equation n equals to 3m, which m is element of Z. So in A2, we could substitute the equation in A1 to 2n squared minus 3n. And then after we expand it, we're going to get 18m squared minus m. After that, we're going to factorize it, and then after we factorize it in A3, we're going to get 9 in bracket 2m squared minus m. And then the equation in the bracket, we need to let it as k, and in A4 we're going to get the same answer that we just stated in B1. So for the last example, the question given, if the triangle RST with side of length r and s and hypotenuse of length t satisfy t equals to square root of 2rs, then the triangle of RST is isosceles. So the hypothesis of this question is the right triangle RST with side of length r and s and hypotenuse of the length t satisfy t equals to square root of 2rs. For the conclusion is the triangle RST is isosceles. So for B1 we could wrote r equal to s, and for the B2 we could wrote r minus s equals to 0. So for A1 we could write t squared equals to 2rs from the hypothesis t equals to square root of 2rs. And then in A2 we're going to use Pythagoras theorem, which is going to be written as r squared plus s squared equals to t squared. And in A3 we just substitute A1 into A2. For A4 we're going to obtain r squared minus 2rs plus s squared equals to 0 from the A3 by algebra. So in A5 we're going to factorize z equals to r minus in bracket r minus s squared equals to 10. And for the last one we're going to get A6 equals to r minus s equals to 0 from A5 by algebra. As the conclusion that can be made from this presentation is, to summarize, by identifying the main problem and also the conclusion that need to be proven, we can apply the appropriate proof, proposition, or mathematical statement using basic law and perform, plan, conduct, and analyze outcome of truth and falsity of the statement, laws of logic, and use of the truth of the table to show the validity of the arguments.
And this is our reference. Wait.
That's all for us. Thank you. Bye.
Okay, class, that's all for today. Class dismissed. Thank you, madam.
Thank you.